12th International Physics Olympiad year 1981 IPHO. I offer private tutoring for Physics Olympiad preparation. I currently have openings. Message me if interested. My email is fred1996@hotmail.com, or you can use Skype name Eduard F 1996. Problem number 1. A static container of mass big M and cylindrical shape is placed in vacuum. One of its ends is closed. A fixed piston of mass small m and negligible width separates the volume of the container into two equal parts. The closed part contains n moles of monatomic perfect gas with a molar mass m0 and temperature T. After releasing of the piston, it leaves the container without friction. After that, the gas also leaves the container. What is the final velocity of the container? The gas constant is R. The momentum of the gas up to the leading of the piston can be neglected. There is no heat exchange between the gas container and the piston. The change of the temperature of the gas when it leaves the container can be neglected. Do not account for the gravitation of the Earth. Solution for problem number 1. Up to the moment when the piston leaves the container, the system can be considered as a closed one. It follows from the laws of the conservation of the momentum and energy that we have these two equations, where V1 is the velocity of the container when the piston leaves it, and U velocity of the piston in the same moment. Delta U, the change of the internal energy of the gas, and the gas is perfect and monatomic, therefore we have delta U equal 3/2 nR delta T, which is 3/2 nR multiplied by T minus Tf, where Tf the temperature of the gas in the moment when the piston leaves the container. This temperature can be determined by the law of the adiabatic process. It means that PV power gamma is constant. Using the perfect gas equation, PV equal nRT, one obtains PV equal nRT, and from here we have TV power gamma minus 1 equal constant. It means that TV power gamma minus 1 equal TF power gamma minus 1. So here we use a relation that V final, Vf equal 2V initial, and the fact that the adiabatic coefficient for one atomic gas is equal 5/3. The result for final temperature is next one. T final equal T multiplied by 2 power negative 2/3. Solving the equation 1 and 2, we have U equal this expression, and now we can put this U to the second equation and find total dependency. Here we have equation to find what is V1. That will be expression number 5. If the gas mass M0 is much smaller than the masses of the container M and the piston M small, then the equation 5 is simplified to 5 prime, which is this one. Now let's rewrite this equation 5 and 5 prime. We will use them later. Now when the piston leaves the container, the velocity of the container additionally increases to value V2 due to the heats of the atoms in the bottom of the container. Each atom gives the container momentum P equal 2ma multiplied by Vx average, where ma is the mass of the atom and the Vx average can be obtained by the average quadratic velocity of the atom. So for average quadratic square we have this expression, and because all these components are equal to each other, finally we have Vx average equal this expression, or P equal this expression. All calculations are done assuming that the thermal velocities of the atoms are much larger than the velocity of the container, and that the moment is described using system connected with the container. Have in mind that only half of the atoms hit the bottom of the container. The total momentum received by the container is Pt equal 1/2 n Avogadro multiplied by P, which is n m0 multiplied by square root from average V square over 3. And the additional increase of the velocity of the container is V2 equal Pt over total mass, which is n multiplied by m0 over m multiplied by square root from V average square over 3. So now we can use the formula for the average quadratic velocity. That will be square root from 3RT over m0. As well, equation 4 for the temperature Tf. So here we can use final temperature Tf, and the final result for V2 will be this one. Expression number 8. Therefore, the final velocity of the container is V1 plus V2, which equal this expression. Therefore, the final velocity approximately will be last one expression. That was solution for problem number 1. 12th International Physics Olympiad, year 1981, IPHO. I offer private tutoring for Physics Olympiad preparation. I currently have openings. There is a discount for group classes. Message me if interested. My email address is fred1996@hotmail.com and the Skype name Eduard F1996. Problem number 2. An electric lamp of resistance R0 equal 2 ohm working at a nominal voltage U0 equal 4.5 volt is connected to accumulator of electromotive force E equal 6 volt and the negligible internal resistance. Question number 1. The normal voltage of the lamp is ensured as the lamp is connected potentiometrically to the accumulator using a rheostat with the resistance R. What should be the resistance R, and what is the maximal electric current I max flowing in the rheostat? If the efficiency of the system must not be smaller than eta 0 equals 0.6. Question number 2. What is the maximal possible efficiency eta of the system, and how the lamp can be connected to the rheostat in this case? Solution for problem number 2. Tensiometer is a 3-terminal resistor with a sliding or rotating contact that forms an adjustable voltage divider. If only 2 terminals are used, one end and the whether it acts as a variable resistor or rheostat. Question number 1. The voltage U0 of the lamp of resistance R0 is adjusted using the rheostat of resistance R, which is this one plus this one. Using the Kirchhoff laws, total current I equal U0 over R0 plus U0 over R minus Rx, where R minus Rx is the resistance of the part of the rheostat parallel connected to the lamp, and Rx is the resistance of the rest part. So it means that we have also U0 equal E minus I multiplied by Rx. The efficiency eta of such a circuit is power on the lamp over total power, which is equal to U0 square over R0 divided by IE, or this equation. From equation number 3, it is seen that the maximum current flowing in the rheostat is determined by the minimal value of the efficiency. So we have I maximum equal U0 square over R0 E eta minimal, or this one, because eta minimal equal to eta 0. The dependence of the resistance of the rheostat R on the efficiency eta can determine replacing the value of the current I obtained by equation number 3. That will be I equal U0 square over R0 E eta. And now we can use this expression to put in equation number 1 and equation number 2. So we have equations number 5 and 6. Then, using Rx and put it in equation number 5, we can calculate what is R. That will be equation number 7, which showing how is total resistance R depend from efficiency eta. To answer the question number 1, the dependency R from eta must be investigated. By this reason we find the first derivative, which is this expression. Now after doing this we will find that first derivative must be equal to this expression, and here, because denominator is positive, we need to find what is the sign of the numerator of this fraction. That will be this expression, and because eta is less than 1, we will find that this expression is positive. So it means that first derivative is positive. Therefore the above derivative is positive and the function from R from eta is increasing. It means that efficiency will be minimal when the rheostat resistance is minimal. Then after putting numbers we have R minimal equal this expression, or about 8.53 ohm. The maximal current I maximum can be calculated using equation number 4. The result is I maximum approximately equal 2.81 ampere. To find the answer for the second question, we can see that as the function R from eta is increasing, so when R going to infinity, eta maximum going to U0 over E, which is equal 0.75. This case can be realized connecting the rheostat in the circuit using only two of its 3 plugs. The used part of the rheostat is R1 equal E minus U0 over I0, which is about 0.67 ohm. So that was a solution for question number 2, and this is total solution for problem number 2. 12th International Physics Olympiad, year 1981 IPHO. I offer private tutoring for Physics Olympiad preparation. I currently have openings. There is a discount for group classes. Message me if interested. My email is fred1996@hotmail.com and my Skype name is Eduard F. 1996. Problem number 3. Detecting astronomical radio waves. A detector of radio waves in a radioastronomical observatory is placed on the sea beach at a height h equal 2 meters above the sea level. After the rise of a star, radiating electromagnetic waves of wavelength lambda equal 21 centimeters above the horizon, the detector registers a series of alternating maxima and minima. The registered signal is proportional to the intensity of the detecting waves. The detector registers waves with the electric vector vibrating in a direction parallel to the sea surface. Question number 1. Determine the angle between the star and the horizon in the moment when the detector registers maxima and minima in general form. Question number 2. Does the signal decrease or increase just after the rise of a star? Question number 3. Determine the signal ratio of the first maximum to the next minimum. At the reflection of the electromagnetic wave on the water surface, the ratio of the intensities of the reflecting field of the refracted ER and the incident EI wave follows the law ER over EI equals n minus cosine phi over n plus cosine phi, where n is the refraction index and the phi is the incident angle of the wave. For the surface air water for lambda equal 21 centimeters, the refraction index n equals 9. Question number 4. Does the ratio of the intensities of consecutive maxima and minima increase or decrease with the rising of the star? Assume that the sea surface is flat. Solution for problem number 3. Question number 1. The signal registered by the detector A is a result of the interference of two rays. The ray 1, incident directly from the star, and the ray 2, reflected from the sea surface. See the figure. The phase of a second ray is shifted by pi due to the reflection by the medium of a larger refractive index. Therefore, the phase difference between the two rays is delta equal AC plus lambda over 2 minus AB, which is finally lambda over 2 plus 2h sine alpha. The condition for interference maximum is lambda over 2 plus 2h sine alpha maximum equal k lambda, or sine alpha maximum equal 2k minus 1 multiplied by lambda over 4h, where k equal to 1, 2, 3, etc. till 19. The difference of the optical paths cannot exceed 2h, therefore k cannot exceed 19. The condition for an interference minimum is lambda over 2 plus 2h sine alpha minimum equal 2k plus 1 multiplied by lambda over 2, or sine alpha minimum equal k lambda over 2h, where again we have k equal 1, 2, 3, etc. till 19. So that was a solution for the first question. Question number 2. Just after the rise of the star, the angular height alpha is 0. Therefore, the condition for an interference minimum is satisfied. By this reason, just after the rise of the star, the signal will increase. That was a solution for question number 2. Question number 3. If the condition of an interference maximum is satisfied, the intensity of the electric field is a sum of intensities of the direct ray EI and the refractive ray ER, respectively. So we have E maximum equal EI plus ER, and because ER equal EI multiplied by n minus cosine phi over n plus cosine phi, we have E maximum equal EI multiplied by 1 plus n minus cosine phi over n plus cosine phi, and because phi maximum equal pi over 2 minus alpha maximum, we have E maximum equal EI multiplied by 2n over n plus sine alpha maximum. At the interference minimum, the resulting intensity is E minimum equal EI minus ER, which is EI multiplied by 2 sine alpha minimum over n plus sine alpha minimum. The intensity I of the signal is proportional to the square of the intensity of the electric field E. Therefore, the ratio of the intensities of the consecutive maxima and minima is I maximum over I minimum equal E maximum over E minimum square, which is this expression. Using the equation 2 and 3, the equation 6 can be transformed into the following form. Expression for number 7 is the result when we insert alpha maximum and alpha minimum from the expression 2 and 3. And that was our result. Using this general formula, we can determine the ratio for the first maximum K1 and the next minimum. For the equation number 8, we have K equal 1. It means that I maximum over I minimum equal this expression, and after putting numbers, we have this ratio is about 3 multiplied by 10 power 4. That was solution for question number 3. Question number 4. Now, using formula number 7 and n much greater than lambda over 2h, we have approximately that I maximum over R minimum equal 4n square h square over k square lambda square. So with the rising of the star, the ratio of the intensities of the consecutive maximum and minima decreases. So that was solution for question number 4, and now we did all questions for problem number 3.